Recording. Okay, welcome everyone. As Dr. Spania said, my name is David Ramirez. I'm going to be talking today about 3D reconstruction, some of its origins, and some of the current state of the art, especially with regards to deep learning. The context is some of my applications-focused research. And I'll talk a little bit about that in this presentation. Okay, so the topics for discussion today, I'm going to do an introduction to 3D reconstruction, some of the terminology and how it intersects with adjacent fields of study, including structure from motion and visual SLAM. I'm going to talk about what are some of the limitations and problems with the current state of the art, and where is the applications within industry right now. And then I'm going to get into the main topic of discussion, which is these techniques, survey of these state-of-the-art techniques, and some of the research standards that many people use as benchmarks. A little bit about myself before we get started. As Dr. Spanias mentioned, I've been with the SenSIP lab for 7 years. And during that time, I've been very hands-on with machine learning and neural networks. I've been at ASU for far too long, but I enjoy the research that we do here. And I am making steps slowly as a part-time PhD student while I work in industry. I have quite a lot of work in my 9-to-5, but the research here that I'm doing is supports some of that effort. What is 3D reconstruction? Well, there's a lot of related nomenclature. If you're from the robotics field of study, you may be familiar with the term visual SLAM, certainly. If you're more from a traditional computer vision background, you may be more familiar with the term structure from motion. It's really evolved from being specifically about motion, and I'll explain some of those differences in a moment. There's also other related terms related to, sometimes you'll hear tracking and mapping, TAM. Excuse me, could you please mute? The industry nomenclature for a lot of this mapping technologies is called photogrammetry. I'll explain that in a moment on what exactly that is. And then a lot of the basis for this field of study is based in multi-view stereo, and I'll explain more about that. The objective of all of these different nomenclature and techniques is to observe 2D imagery and estimate 3D structure. So there's very little difference in what the objectives are and what the inputs are. How you get to from step 1 to step 2 can be very different though. Okay. Let's see. All right. So more terminology. Multi-view stereo, certainly in the 90s, had a fixed camera setup, calculating the three-dimensional structure between cameras with known distance from each other, something that's often known as a foundational matrix between the two views. That evolved into the terminology structure from motion. If you have one moving camera, or perhaps still two stereo cameras as they move, can you generate the three-dimensional structure of the scene? And slowly over time, that field of study evolved to more of unconstrained photo collections. Images gathered online from different cameras with different camera characteristics, perhaps also with unconstrained environmental conditions, different times of the day, different visual effects on the imagery. But again, the goal here is to generate that three-dimensional structure. So it might be used in other follow-on activities like perhaps video games or entertainment media or augmented reality, virtual reality. So that industry nomenclature, photogrammetry, it has its roots within this structure for motion from potentially unconstrained photo collections. A lot of surveying techniques that are used in industry, they might actually do better if they are more controlled photo collections from a consistent camera, especially if there's additional sensor measurements present. But photogrammetry is very much structured for motion for most intents and purposes, as structures for motion is used. For this example image that I've got here on the slide, this demonstrates this correspondence point matching. Multi-view stereo, usually, and also structure for motion almost exclusively in the traditional sense. They look at multiple images, look for those correspondence points, these blue points on the image frames, and then using those, they use geometry to trace rays into the environment, make sure that those rays intersect at common points. And so the math basis here is for all of the correspondent points, little x, you would like to know the camera position, the projection matrix from that point, pinhole camera P out into the three-dimensional environment, big X. So you're trying to invert and solve for this this P while holding X and solving for that jointly. In practice, though, you often run into problems when you don't have perfect correspondence between points. Some points are going to be occluded from certain views. Structure for motion has grown from those challenges, and robust point selection and in correspondence matching and pseudo matrix inversion and optimization are a big part of the traditional structure for motion pipeline. And we'll talk about that in a little bit. All right, more terminology. So what I failed to mention here in that really simple matrix inversion problem setup is this camera rotation, which is the other half of camera position. If the camera is not constrained to an orthogonal world basis, then and it rotates in the three-dimensional rotations, which are known as, oh, I think I deleted it here. Oh, it's not showing correctly. But they're known as yaw, pitch, and roll. Those three directions of freedom for rotation, those become a challenge to represent mathematically. So you can take a basis function, three-dimensional Euclidean space, and rotate that in any way you want to represent the camera rotation. But that has unlimited degrees of precision, and so there's a lot of it's not a great solution for mathematics. So that basis rotational matrix not often used. What are often used are these quaternions, if I'm saying that correctly. You can think of these as imaginary numbers, as the INQ, in phase and quadrature, are to radio frequency signal samples. In the time domain radio frequency field of study, we have INQ, in phase and quadrature, both a real and imaginary component. This quaternions representation takes the three-dimensional representation, adds a fourth dimension as is necessary, and And now you've got this A, B, and C values that you can represent a rotation of a camera's movement. So this is often preferred within geometric 3D reconstruction pipelines. But another one that's more often used in applications is these Euler angles, which are the yaw, pitch, and roll. With both the three-dimensional Euclidean position of a camera, the X, Y, and Z coordinates, and these 3 dimensions of rotation, you have these 6 degrees of freedom for any camera. That determines the camera's placement and orientation. There's other variables that you would like to solve for cameras, part of the camera calibration process, but I'm not going to discuss that here today. Finally, there's this idea of bundle adjustment. There's a big field of study here. You optimize both your 3D points in space along with your camera pose. You optimize for both of those variables. Once you have a closed loop solution where you can bounce between multiple frames of reference and optimize for all of the views jointly. I'll talk about that more in a little bit. There's often this idea of local bundle adjustment within very similar images, and then a global bundle adjustment that's used for optimizing large graphs of measurements. All of that has built up structure for motion, but into this idea of visual SLAM. So SLAM is simultaneous localization and mapping. We're localizing a camera and we're mapping the environment. SLAM might be driven from LiDAR measurements, purely 3D points, or they may be driven by visual imagery and video, which is what I'm going to discuss today. Visual SLAM is often the nomenclature within the robotics community because of the need for this sort of specialized technique to be real time and generate point clouds within the near field around a robotic agent as to avoid collisions. Visual SLAM is often not focused on mapping. They just want to track points in space for brief periods of time for safety and motion control, but not necessarily for mapping. And I'll show you some of the limitations of visual SLAM algorithms here shortly. I believe on the next slide, I have an example of a visual SLAM pipeline. So this, as you can see, actually, I'm going to stop my presentation and I'm going to reshare so that I get it just quite right. I imagine that this is not well optimized for video. So let me do that really quick. Optimize for video. Okay. There may be a little bit more latency delay, but this should be a cleaner video for you as the audience. Here in this example, we have a recent 2020 example of a visual SLAM pipeline. It's not what I am focusing on for some of my research for a few limitations here. You can see that on the right that the point clouds are being added to perhaps on a second by second basis for this video. It has many points of interest that it calculates on each frame of that video in the upper left quadrant, and in the lower left quadrant you can see the green points which have contributed to good correspondence and good geometric verification, and then there's other colored points like reds, perhaps blue points where it might have been a false positive match. The imagery, although the feature points may have generated a match, the geometric verification may have denied those because it didn't make sense within the rest of the context of the scene. View to view, solving for both the triangulation of the points and the position of the camera. All right. Finally, one of the limitations of this sort of pipeline, as I said, it's very focused on the near field. Even for autonomous driving applications, you don't rarely look further out than might affect your performance on the road. There's no need to map objects that are in the far field away, but that is a focus of some of my research. All right, so I mentioned some of these limitations already. When you're calculating feature points within the environment through different techniques like SIFT or SIRFT or Orb, those have view-dependent effects, reflections, and things like translucency. They cause pixel differences from different angles of view. If there's a strong lighting source and a reflectance off of a certain object, that might be more pronounced from some angles more so than others. That's within the Visual SLAM context. Also, within the structure for motion on unconstrained image collections, if it's different times of the day, if there's different shadowing conditions, if there's warm lighting or cool overcast clouds, all of those have an effect on the RGB pixels that we might want to generate correspondence on. And all of those affect our ability to do so and match those points. So that's a limitation of feature point matching. The next one here is scale ambiguity. You can do all this math, you can solve for the camera positions and solve for the 3D points in space, but you really don't have any context about what the true scale of the scene is. I hear somebody eating their microphone. If you don't mind putting yourself on mute, I appreciate it. The scale ambiguity is, well, that could be a large object far away from all of our cameras, or it could be a small object very close to all of our cameras. You don't get a sense for the real scale with some of this geometric solutions. Next, moving objects. Moving objects are a big problem. You can generate a lot of correspondence points on things like vehicles. The shapes of the vehicles don't change, but their position within the world does, and that generates a lot of discrepancy from the rest of the static scene that you would like to map. Next one here, search complexity. When you're doing this feature point matching, the scale of that search, how many points you want to track over time, it scales quadratically with features, and it also scales, I believe, linearly with the number of images. So if you have a bunch of image frames and you want to keep building your map over time and keep tracking more and more features, you're going to run out of computer memory pretty quickly. And not only that, but the search to find those matches has a lot of computational complexity for adding more. So it slows you down. That speed is very inconsistent and unpredictable because this is a search strategy. So you don't have guarantees on when you're going to find that correspondence in the search. So those are problems. And I don't say it explicitly here in this presentation, but I'll just go and say it right now. A big advantage of deep learning solutions, they may not be as fast as some of the geometric based approaches can be, but they're very consistent in the runtime. You have pretty good guarantees on how long that runtime is going to be every time you hit a new video frame on your neural network or deep learning solution. So that's a really big advantage, and you'll see that in some of the solutions that come. So what is our problem? What are the things that we would like to overcome with some of this research? Well, with traditional structure from motion, you don't have real-time speeds. You're taking all of your data offline, whether it's an unstructured photo collection or something that's more structured from consistent video frames. But you're taking all of that, and it often takes hours to optimize and find these correspondences and build out a scene graph and register and build out a three-dimensional scene on the course of hours. So definitely not real-time speeds. Visual Slam, on the other hand, has, as I've shown, can be real-time speeds, but the mapping quality is very sparse. You're only looking at things that are close by. You throw away things that are far field that maybe you don't have a good difference frame to frame to calculate that, triangulate that point that's way out there in the far field. But you maybe could if you took frames from big differences apart. So you would like to increase both some of the limitations that I mentioned on the previous slide, but also just denser point cloud quality. This approach here, then, the terminology, it may not be structure for motion then, which has certain basis of study. It may not be Visual Slam, but I believe that the terminology maybe should be 3D reconstruction. We'd like to do it in real-time speeds like Visual Slam, but we'd like to have good mapping quality, good reconstruction. So I believe 3D reconstruction here might be the right nomenclature. So this needs those real-time speeds and improved mapping quality. So what are some of the current solutions that exist in imagery? So in this industrial example, you've got a drone flying overhead. It's taking a bunch of pictures. You can sort of calculate where those image frames are and solve for the three-dimensional structure of the ground underneath. The problem is the more images you take, the longer the computation is going to be. The higher quality certainly is going to take longer, but just having more images takes a long time. You can't run this with a lot of these products sequentially. It's take everything at once and optimize for everything jointly. But I'll talk about why it is possible to do this sequentially. It's an open question why that's not being done more in industry right now. So I'll explain some of that in a minute. So now we're going to get into these techniques, survey, these best-in-class techniques, some of the state-of-the-art. I wish I had a water bottle nearby. If you don't mind, I'm just going to grab one really quick. Unprepared.
We cannot bring you one, but
okay, excuse me. All right. Yes.
Oh, go ahead. I was just making a joke that we cannot get you one through Zoom. But
is my video still coming up through okay?
yes, it's fine.
Okay, so the survey of some of the best in class and state of the art. So you'll often hear COLMAP is a structure from motion benchmark that's used in a lot of papers in the age of deep learning. COLMAP, which is from the paper Structure from Motion Revisited in 2016. This has a lot of basis in this unconstrained photo collection. The paper doesn't say it explicitly, but I believe COLMAP is meant to mean collections of images mapping. It has this deep algorithmic sequence, which I'll touch on here in a moment. But this is that sort of very complicated traditional geometric structure from motion pipeline. in some of the earlier work, you can see that they take images from tourists, and I believe one of the papers is called "Building Rome in a Day," because to register and find all these feature point correspondences between images may often take 24 hours of computational time to render a sparse point cloud like this. There's some limitations there, but this ColeMap implementation, which has become very popular and used as a benchmark, it added a lot of features for speedy optimization, and let's get into that. So the algorithm sequence here is feature extraction. You could use features of different types. I'm not. I have a trouble recalling which type of feature they use explicitly within this research. But from that feature, you can build certain search trees to find faster feature matching. So instead of it being an O squared complexity, you could get something less than that. That helps you do the matching offline. You've got all of your images, you pre-compute all these features, and then you want to match the features together. How many features match in the different images. This is all done offline before any 3D reconstruction. Then, when you know a little bit more about the similarity between different images in your collection, you can estimate this fundamental matrix and do something very similar to what's done in traditional stereo vision. You take one frame of view, you take another frame of view, you want to estimate the difference in those sort of basis functions to get you from one to the other. With that being done, you can take the similarity matches and also these fundamental matrices and generate a geometric, you would want to generate a scene graph then next. But there's a little bit of geometric verification to make sure that to make sure that those feature points that did match, that they actually make sense. So with a scene graph, you've got a graph structure that connects all of the, or strongly connects some images within your collection, the ones that have the most correspondence. So you would like to find group images together that have high correspondence matches. And then from that scene graph, you can iterate over all of your images, slowly build out your scene, and hopefully avoid some of the pitfalls of these techniques. One of which is initialization. With that scene graph built, you have this similarity between all your images. You want to pick two images that have corresponding features that will be a starting point for your 3D reconstruction. So you take those two images, you solve just as we did in some of the very early math of this presentation. You solve for the camera position, rotation, and also you solve for those points in the three-dimensional space, which registers your first three-dimensional points within the scene. From there, then you need to do a next best view selection, which is aided by the similarity search and scene graph that you did prior. So you can do that quickly to find the next best view, the one with the most corresponding features to the graph that's already, or to the three-dimensional scene that's already been rendered. With that next image, you register it into the existing point cloud, you triangulate those points, you set the new camera position of that new image, and then you continue to iterate in this process, adding the next image, making sure it matches to the existing scene, calculating the position of the camera, and so on and so forth. ColeMap adds a couple optimizations here related to redundant views. It will prune potential views out of the scene if they seem unnecessary. It'll prune things from the search if they're not helping. Then there's this bundle adjustment phase, which is very important for geometric optimization. And you do that both at the small scale within very similar images, but then also at the large scale, especially when you can bounce around between 3 points with some correspondence within all of them, or more than 3 points. If you have a long chain that loops, there's a loop closure, and you have feature points that overlap into all of those images. So this is the CoLMAP implementation. It's very, very popular, and it's used as a baseline within a lot of modern research. This is an example of CoLMAP as implemented in some open source software. So in this example, they took this unconstrained image collection and they pre-computed all of the feature points that may exist in there. And then they also pre-computed all of the matches and this similarity graph. Here you can see how one image closely matches to other images. And then in close to real time, you can then build out a scene from those new images. It grabs a new image, it registers it into the scene, it finds those correspondence with the existing points in a three-dimensional point cloud, and you're building out your scene over time. This runs pretty quickly once you've done all that feature point matching, which is computationally hard. Finally, when you get deeper into this, let's see, I don't think I want to watch all the way to the end. But you can finally get to a high dimensional, something greater than a sparse point cloud. You can render out all of the additional structure of the scene with CoLMAP. Once you've done, you've got all the camera positions and you've got a basis with some sparse point clouds. I'm going to keep moving here. Okay, so the next state-of-the-art example that I'd like to explain is this Orb Slam framework. Orb Slam 3 was published in 2020 and 2021 was accepted into a conference. This is done by the researchers at the Zaragoza University in Spain. This follows very similar geometric reconstruction as traditional structure per motion, with some additional features added, and you don't need the initial pre-compute stages that CoLMAP had. You don't have to pre-compute all your features and find matching and find a scene graph and all that stuff, because you don't have that in a Visual Slam application. You're taking frames of video one at a time, and you're building out your three-dimensional scene with whatever it gives you, in using both the local in time and space feature points, but also then going back to earlier measurements, so you can generate three-dimensional structure from, if you want to call it, historically old measurements, which might be minutes ago, or they might even be things that were taken at other points in time during different recordings. That's this idea of an atlas, which is implemented by Orb Slam. So I'll give an example of video of this in a moment, but this follows a very traditional, I guess if you want to call it, stereo, multi-view stereo geometric reconstruction pipeline. So you're doing feature extraction, you're tracking local keyframes, the best images from the video. You get your key points from those. You discard the frames of videos that are blurry. Once you've got some key points from a key frame that you're tracking, you want to triangulate your new measurements into that existing those points. So you're not doing 2D your new image frame into a 3D world, you're simply doing 2D to 2D. You're comparing your new image to the keyframe image and making sure that those are still relatively consistent. From that, you can get a little bit of camera pose relocalization as you go, but eventually you're going to hit a point where you need to make a new keyframe because the camera track has moved greatly from the original keyframe. Your view of the scene has changed greatly. So you would register a new keyframe, and then it's at this keyframe level at the far right, the local mapping stage, where you're comparing keyframes together, and then you're doing that geometric comparison. So you're taking good frames of video, you are projecting those correspondence points into the three-dimensional space, and you are jointly solving for your camera positions. While you do that, you can do local bundle adjustment to optimize for those conditions. As you move further out and generate more data, this idea of loop closure becomes very important. If you can close the loop on all your points, if you can have one of your earlier measurements now has some correspondence with one of your new measurements, that link can close the loop in all of your measurements, and that can let you optimize in this global bundle adjustment strategy. So that it's very important for optimizing this sort of framework. And the idea of map merging extends that further. If you have some past maps with keyframes and key points that you would like to find correspondence on, you can do so by searching through a database of old measurements and old maps, this idea of an atlas. So all of these things add functionality to Visual Slam pipelines. This Orb Slam 3 allows for a lot of variation for fisheye lenses and stereo cameras and inertial measurement units. So it adds a lot of features, but the base of it is very similar to the standard structure for motion geometric pipeline. All right, I'm gonna take a sip of water. But while I do, please enjoy this video. This is the Orb Slam 2 implementation. And you'll see here, this is the KITTI data set, the autonomous driving data set. So that's a little bit faster. It's 5 times faster than real speeds, but it's doing that in something real time. Orb Slam 3 runs really fast. The problems occur when you want to do maps and atlas of maps, and because that increases the search space. The more past measurements that you have, the larger your scene, the more features that you're trying to track and match. All of that adds complexity and slows you down over time. There's not much you can do about that within this search strategy, which is feature point matching. All right, I'm going to keep moving here. You can see that it generates a sparse point cloud. Only the points that are tracked contribute to the three-dimensional structure of the point cloud. So that's very sparse. You have enough to track most objects so long as they have some good feature points, but otherwise you don't have good structure on your scene. And then, as we mentioned before, the feature points break down from different view dependent effects. So that being said, introduce neural radiance fields, which is the hotness right now. So neural radiance fields, Nerf, was proposed last year by Google and Berkeley researchers. What it is it's a rendering pipeline that takes images as input, very similar to structure for motion task. It can then render out the three-dimensional scene and you can render views from new angles. Perhaps it's best to start with the video here, and then we'll come back to the video. So Nerf here, you might take a small number of measurements, and then the neural network then allows you to render out additional images from any potential view that you might want, any potential view, which is incredibly powerful. I'm going to go back. So what the pipeline here is you draw rays through your image pixels into the scene. We're not doing feature point matching though. What you then do is for a particular ray, you sample across that line at whatever interval you want to sample. Maybe you want to have a really high precision rendering. Maybe you want to have something of a rougher estimate. You can pick how often you want to sample, and that's represented by these dark dots in the line. Then for each one of those sample points, you pass them one at a time into the neural network, which is represented here by this fully connected network. It's a really simple neural network. You almost can't mess it up. Next, it generates, all of this thing is meant to do is for a particular point in space, which you gave it one point at a time, and the view that you're coming at from, the two-dimensional angle, I guess that would be pitch and yaw. You don't do roll here in this case because a ray does not have a roll axis, or it has an axis, but it doesn't have a roll effect because you're just looking at a single line. You pass in those view-dependent effects, which is which angle you want to view the scene from on that ray. And then the neural network will tell you what the color is at that point that you asked for. And also this other parameter here, which is known in the paper, I believe, by, it's a volumetric effect. It's something like translucency, opacity. Is there something physical structure at that point in space? And you can sample as often as you want. The thing is, this process can be pretty slow, right? You may have an image with 1,000 pixels on it or more. That's 1,000 different rays through the scene that you're trying to draw for each one of those pixels. And then there's how often do you want to sample on that line? If you want a high degree of precision for your rendering, you need to sample a lot on that line. And that's also very complex. So this is not something that can be run in real time. But once you've generated this volumetric information for each one of those points on your ray, then you add them all up together to render out this pixel. As with neural networks, they let you learn from examples, and you minimize the loss between the original image that you used and the image that it rendered out. So really cool stuff. You aggregate all those points on a line that you sampled, and then you minimize that loss between the ground truth pixel and the rendered pixel. So just using normal rendering techniques, you just, whatever thing came first, that's the thing you see the most of based on its opacity, based on translucency, and then you render however much you need to figure out what's there at the volumetric level. So I'm going to play the full video now for Nerf. Again, you can see that it's rendering out images from novel viewpoints, very much to the same effect of a structure for motion pipeline, but with some limitations, and I'll touch on that for a second. Here you can see it's drawing the line through the image, through one pixel, and then we sample on that line at some regular interval, perhaps. It could be anything. The neural network allows you to take any real valued measurement on this ray. So it doesn't have to, it's not a voxel representation. It's not a Minecraft little 3D pixel out in space. You can sample at any interval you want as finely as you want to generate that three-dimensional structure. Then, with enough views of the scene, the neural network will learn over time every view from that scene, and it naturally is able to interpolate into novel views. Here you can see some of the previous state-of-the-art in previous years, and then Nerf rendering out novel viewpoints. I think I'm going to stop this video here and move on to the next one. Let's see if it will let me. So there's been some really big interest in Nerf in the last year's time. And by the same authors, they released a second implementation here, which is called Nerf in the Wild. This takes an unconstrained photo collection, very similar to the structure from motion pipelines that we saw previously. It learned that transient information about tourists in the video, or tourists in the images, or other transient effects, time-dependent things that might be occluders. It learns all that, calculates an uncertainty, learns an uncertainty measurement, and then there's also view-dependent effects that are baked into this reconstruction process. So it follows the same Nerf pipeline, but it's got a couple other variables that it learns along the way. What this allows you to do then is render the scene from a variety of different color views, which is pretty impressive. Here you can see the three-dimensional structure of the underlying scene. And then I think in a moment here, it's going to start playing some view-dependent effects. So perhaps at night, there's yellow lighting, depending on different cloud cover and different times of the day, the shadow effects and color effects on the scene can be vastly different. The neural network captures all those view-dependent effects, those environmental conditions, embeds it into a latent representation, and you can interpolate across those different latent representations, very similar to generative adversarial networks, if you're familiar with latent space interpolation. All right, that's all I'll play here. Okay, water break. I'm gonna do my time. Oh man, I'm almost at my hour. So I got two more that I want to get to, and I'll do them fast. Oh, there's gonna be no time for questions. So Monocular Reconstruction, Monorec, was released earlier this year. It's not a huge breakthrough. It just combines a bunch of different simple approaches to try to build better depth and three-dimensional structure calculations. So what this thing does, using 2 frames of a video, 2 images, it looks for how much variation there is between those 2 frames. Yes, as you move, everything's changing a little bit, but just some normal optical flow type of processing, some pixels are changing more than others. And even more so, if there's moving objects within the scene, like other vehicles, or even things that aren't moving in the video because you're moving at the same speed as the other vehicle, those things are past, those view-dependent, they're not view-dependent, those variance information, photometric variance, those are passed into as additional inputs to a masking object detection framework. So very similar to RCNN, mask RCNN, object detection with mask outputs. You're trying to calculate where that moving object is in the scene on that other vehicle. You do that so that you don't accidentally render out three-dimensional structure on that moving object, because that would just add noise and to your three-dimensional map. Next, second stage, very simple. You take that mask, you add it in with some of your other variance information in the original image. You pass it through a depth module on the same vein as dense depth, mono depth, all of those different monocular depth estimation frameworks. And then this will then render out a depth map, which can give you three-dimensional structure. But you've removed the moving object, the other vehicle, which might have caused problems and noise into your rendering, three-dimensional point cloud. So I'll put an example really quickly. So the problem with these type of rendering, three-dimensional structure generation pipelines, like dense depth, like mono depth here, like mono rec, is they generate these points. They generate a lot of these points, one for every time you hit the neural network, but they never explicitly merge points back together, right? If you have several points that have been generated into a certain area, those never get merged back together. There's no correspondence. It's not refining measurements over time. It's not really cleaning up the three-dimensional structure. It's just adding on top of it every time, which is a problem. I haven't seen a lot of dense depth type frameworks, which then try to extract and simplify some of this these point clouds that just add additional complexity on top of each other. So that's maybe something that has an opportunity for advancement. So the video basically, it shows, hey, we did a good job. But the points clouds are very, there's a lot of them, and they add more complexity to the scene. Okay, running out of time. The final video, and I don't have a good explanation for this one, is this neural reconstruction framework. So for augmented reality applications, you need to understand the three-dimensional map, the three-dimensional structure of the scene. So on the right, you can see as this thing looks in real time, it's calculating missing structure in this green dots, as well as three-dimensional underlying structural information. So you could do that with a depth sensor. A lot of modern smartphones have stereo view cameras or even time of flight LiDAR systems now. But you could also do that with a monocular camera, as is important here in this body of research. So hopefully it's going to show some more in a second. This pipeline is traditionally, the problem here is it looks one frame at a time and it generates out point clouds that get messy, they add on top of each other. The advancement here in this research is you look at several frames of video at once. Here's, I think it's talking about motivation and stuff. And I wish I could jump ahead, but I don't think it's going to let me. So depth-based methods, there are scattered results. They're layered on top of each other, as I mentioned. It's a lot of redundant computations because there's not a lot of difference frame to frame. And the advancement here in this body of work is look at several frames of video at once, render out the scene just once, so you're not doing redundant computations. And it does that through a couple of different means, but I don't have enough to explain it here. So I'm just going to call it quits here. So that's my presentation. I think I promised a little bit more, and I'm still working on some additional content. But if you've got any questions, please speak up, and or we can talk offline.
So,
on the
David,
yes,
I've got to run to another meeting, but I will get together and discuss a little bit in preparation for the qualifying presentation. But I think that, please stay on the link. The students and the participants may have questions, but I'll get to meet you a little later next week and we will catch up.
Okay, thank you very much, Professor.
Thank you. Thank you.
All right. Does anyone have any questions or any discussion? Any other cool research that you've seen recently?
Yeah. Hi, David. Thank you so much for the nice presentation. My question is regarding if we have the luxury to design, if we have the luxury to either run an algorithm to do the mapping or create a map, and this algorithm either could run sequentially or non-sequentially. So I give it all of the images all at once, or I could give it one by one. If I would like the same performance, from your experience, which one would yield, would execute in less amount of time?
Sure. So that is one of the advancements in CoLMAP, is this pre-compiling a lot of the hard stuff so that you can do it quicker than if you had done it sequentially. So let's say you took a video camera and you walked the streets of Rome here to the Colosseum, and then you took it back to the video back to your lab, and you wanted to process it in your question. How would you want to do so? Well, you could do it frame by frame. You could say, I'm going to take my first two images. They certainly have a lot of correspondence between them, so I can initialize based on my first two images, my first two non-blurry images. And then I can continue to add additional images in the Visual Slam context. This is not a Visual Slam pipeline, but the math is the same. You could say, I want to build out feature points, 3D points. I want to calculate the camera position. You could keep doing that for frames of video one at a time, but it would be slow. That would be the slower approach. If you instead took all of your frames of video, you chopped them up into images, and you gave them all to this CoLMAP algorithm at the start. It would do all the matching. All that calculation is done in either type. You do the similarity search, which is additional extra computations here. But that gives you the scene graph to tell you which images are most similar and also which images are redundant. If you have a lot of redundant images, which you would have in sequential frames of video, the offline method here that allows you to generate the scene graph, that would tell you there's a lot of redundant frames here. I'm just going to take every 20th frame or every 100th frame. It's not a regular interval like that. It's more of a how much variation is there between the points. But the scene graph in this redundant view mining algorithm elements here, those would allow you to knock off a lot of computations, and they would allow you to do the same quality for faster because you had all that data beforehand and you were able to optimize your search.
And this offline pre-processing does not burden. I mean, the additional cost is not going to make the aggregate total amount of time more.
It's a good question. I don't know if I can answer that definitively, but I would say probably not. I think it's going to be a net benefit if you do the pre-computations. A lot of the professional implementations of this structure for motion CoLMAP, the things that people sell that they use for the industry applications for photogrammetry, they do the offline computations, and I believe they do so because it's faster.
Okay.
Yes.
Yeah, okay. And regarding if I would like to depend on if I have the choice to choose between two sensors, one of them is a basic regular monocolor camera and a depth sensor, let's say, for instance, a LiDAR or whatever. Does the depth sensor add any additional burden, or does it reduce even the amount of time that it requires to generate the same generate the same precision?
It's a good question. With a depth sensor, with a LiDAR system, you get a lot of point cloud information. You have dense point cloud information, but all the points are constantly overlapping on each other, right? You take a measurement once, and then you take a time step away, and you take another measurement. You have depth information from both. You could just add them onto each other, but then now you have so much information in your scene that just grows exponentially that that's a problem. You run out of memory. So you have to merge your points together. And the way you merge your points together is through a SLAM algorithm, through a traditional SLAM algorithm, not a visual SLAM algorithm, but a SLAM algorithm. Is you take your 3D points, you merge them together, you extract the feature points into the three-dimensional real-world scene, and then you track those over time. And then when new measurements come in, you either merge them onto the existing point cloud, or you discard them because they're erroneous, and they don't add additional information useful to your scene. So that's the thing. Having depth sensor is good. You still have to run SLAM algorithm. Then the question is, should you just do visual SLAM instead? Visual SLAM, as I mentioned before, it does not give you dense point cloud information. Not yet anyways. You can do some of the deep learning based techniques like monocular reconstruction. Let's see here, I'm trying to jump ahead. You can do techniques like this, like mono depth, like dense depth. They are somewhat noisy. You may still need a SLAM algorithm on the other end of this to clean up your points and merge them together, as I mentioned. You can't just add points on top of points on every new measurement because you add noise to your system also. So I don't think I answered your question.
No, I think that's it. But after you do this, you take after you run the SLAM algorithm on the depth sensor, on the LiDAR sensor, on the LiDAR data, you can take it after that to improve the map and run and make use of the regular data, the regular visual data that you have, right?
Well, you have to do some camera calibration on the front end to say, my LiDAR system, this is how it matches up with my camera frame. You want to make sure that it's locked in place, right? You can't have a moving camera and a moving LiDAR where they're out of synchronization.
Yes,
so
correct.
You need to understand that. But I don't know all the complexity there. I think it's trivial. I think you can associate the RGB values with the point cloud information, and it's somewhat trivial.
Okay. Thanks a lot for that. Was really very helpful information. Thank you very much.
Okay, sure. You're welcome. Does anyone have another question?
Got a few questions for you, David.
Please go ahead.
You mentioned camera characteristics and camera calibration. Do you see camera characteristics impacting visual SLAM and structure from motion more and more as time goes on, or are camera characteristics, maybe just consumer camera characteristics, but are the camera technologies and characteristics kind of more converging to a point where it matters less and less as time goes on?
Well, let's see. When you do camera calibration, there's a couple of things that you're trying to solve for, and I don't know all the math, but it's the things that you might willingly buy in a camera, right? It's your focal length, it's your angular measurement view. How much of the scene are you actually capturing at what angle? But when you do camera calibration, also you're calculating for nonlinear effects like distortion from a spherical lens. We as humans, we think the world, we look at the world and it looks orthonormal, right? We get straight lines, we interpret them as straight lines. But even as we view the world, depending on our view to an object, right? If you get really close to your screen, the world does bend. Your view of the world does bend. This is even more so exaggerated when you do very narrow focal length lenses, like fisheye lenses, like ultra wide field of view lenses, which have very serious spherical distortion effects. Then you've got problems after that, right? When you have different cameras as input images, different spherical distortions, it may not be a perfectly manufactured lens. There may be other effects there as well, and it's not symmetrical. If you don't know enough about your camera characteristics right there, then even things like depth rendering neural network stuff, right? If you train it one way on one set of data, and then your camera sensor changes, your lens changes and stuff, the field of view is going to be all different. The other nonlinear effects, they're going to be different. It's even maybe more important, because you can train a neural network to learn those things based on your sensor. It's maybe even more important for the geometric pipelines, like the ColMap, like the Orb Slam, because that really affects your math. If you don't understand your camera with a proper camera calibration, then you have problems. Oftentimes, when you're using academic benchmark data sets, they do have some camera calibration baked into them. You say, okay, I'm going to use ColMap, and I'm going to use it on this data set. Well, it's probably already got some pre-compiled camera characteristics for that data set, but it's going to change as soon as you go to the next data set. So, so you're asking me, is it becoming less of a problem? I don't think so. Even little effects for your focal length is just a little bit different than you think. Your field of view is 1 degree more than you think it was. That's 1 degree error on all your measurements. So I mean, that's a big effect. That as you know, that affects that's your what you're trying to achieve, sub 1 degree accuracy or whatever it is. So hopefully that answers your question. I don't know if I have too much more to say.
Yeah, no, that's great.
What else you got, Skylar?
Well, apparently breathing is hard.
Oh man.
I guess just one more. How is the problem of different lighting conditions, like not just day and night, but kind of the different shadows, warm, cool, light, etc., addressed? Like, is there anything clever going on with that, or is that just kind of the, oh, you need to collect more data?
Well, that's a good question. Yeah. I've been hoping to do some neural network generative type stuff where you, like the domain transformation stuff that you see in robotics a lot, right? You train it on this data set. Sun is high in the sky. The shadows are narrow. That's the domain that you wanted to learn. And then you pass in new images, and maybe they have long shadows, or it's got fog effects, or it's got different environmental effects, different coloration. Maybe there's a sandstorm and it's all orange outside or whatever, right? The color information, you're never going to get any feature correspondence. It's super pretty important. And you could force all of your imagery into grayscale, or you could force it into a certain color transformation to try to put it in the same domain, but I don't think that gets all the way there. I think it has to be a learned, a nonlinear learned function that you could do with a generative variational autoencoder. But yeah, I haven't seen too much on that, Skylar. I think you would want to do that. You could do traditional structure for motion pipeline, maybe, if you put it into a simpler representation. So maybe you've got super high resolution video, but the features of the structure of the scene, the quality of the information that you actually need to render out good three-dimensional map, maybe it's less than that. Maybe you just want to pass in the embeddings into your neural network and let it do the rest, so you can compress the inputs. Yeah, I don't know. I have to think about it. I'll get back to you on that one.
Okay, one more, and then I'm done.
All right.
You mentioned using far field points as something that you're looking at. It seems like far field points are less valuable than near field points. So what's the advantage of looking into those far field points, or is that kind of like the point of the question?
Yeah, I think it's if you're really concerned on localization, the localization and the angular triangulation that you can do is going to be more impacted by near field points, right? As you know. But for mapping applications, we can map more of the world. We can know more about the environment. We can track more of the world if we can track those far field points. So that's my interest on far field points. Additionally, there's also advantages for visual odometry drift over time. Yes, you might be able to render out good camera pose based on only near field points, but the minor errors that accumulate over time, the only way you're going to correct that is either with a loop closure or a bundle adjustment, or with far field points that you might be able to capture from different greatly different angles from a old measurement and a current measurement. So I don't know. I think it's important for the large scale application type stuff.
Interesting. Cool stuff. Nice work. I have a lot of respect for survey type work because it requires a lot of looking through papers and digesting a lot. So yeah, nice work.
Thank you, sir. Okay. Any other questions? I'm not sure how many people are still on the call. I see. Just you, Skylar. Skylar and Ruby. All right. Thanks for sticking around, Ruby. Thanks, Skylar, for your attendance. Everybody have
cool stuff. Nice work.
Thank you. Great presentation.
Thanks all. Have a great weekend.
Bye.
Likewise.